Hello team, in this video we will talk about data center networks. So in the way in which we have drawn topologies until now, like we had pods in the bottom and then a hierarchy of switches, one property of this topology is that traffic will aggregate at the upper layers of the topology. 100% of the traffic will traverse this link at the very top, and then if we have P switches on the second layer, 1 over P percent of the traffic will traverse each of the links in this layer. And then if we have R servers inside each pod, we will have 1 over P times R percent of the traffic going over each of these links. And this is assuming perfect load balancing. So one constraint that this will impose in our data center topology is that we will need a lot of bandwidth at the top of the topology. And this topology is usually referred to as a fat tree. So we have fat links on the middle of the tree, and they get bigger as we go up. So cloud providers face constraints when building a data center network. If they need high capacity links, if they want to build fat tree topologies, but link capacities are determined by the technology, and most data centers use Ethernet. And Ethernet is usually available in 1, 10, 40, 100, and 400 gigabits per second. So providers need to design the data center topologies considering how to combine the available capacities. And one trade-off they need to consider is the cost and reliability of high-capacity hardware. So high-capacity links may be more expensive, and they may be around for less time, so they might not be as reliable as more established technologies, or might be less well tested than established technologies. One alternative to high capacity links is link aggregation. So there are hardware devices like routers and switches that allow an operator to establish low capacity links between two devices. Like here we have 10 times 10 gigabit per second links, and we can aggregate them in one 100 gigabit link. And this is done by balancing the traffic arriving at this end across each of these low links, and then on this side, this other device aggregates the data that it receives on each of these links. Although link aggregation is an alternative, it usually requires additional hardware. You need hardware to do the aggregation, and this also involves more cables because each link is lower than a high capacity link. And also, the hardware that is used for aggregation may constrain the number of links that can be aggregated and the capacities of these links. For example, this aggregation device may be limited to 10 links, and each link may be limited to 10 gigabits per second. So you can't build a 400 gigabit per second link, for example, using this aggregation device. So how do we support large volumes of traffic for east-west traffic inside data center without a hierarchical design? So most data centers these days, they use a leaf spine topology. So here we have racks, and on top of the rack we have a switch. We're calling the top of rack switch the leaf in this slide. And then each leaf is connected to multiple links in the spine layer. So here we have 4 switches in the spine layer. So the top of rack switch has 4 upstream links, 1 link to each spine. And this is repeated for all top of rack switches. So this topology allows us to communicate between servers in different racks across different spine switches. One advantage is that this parallelism provides additional bandwidth. So if each of these links is 10 gigabit per second, then we have 40 gigabit per second between any two racks. And to exploit the bandwidth available in leaf spine topologies, we need to employ load balancing. So switches use equal cost multipath or ECMP to balance traffic that's going through them. For example, if we have a server in rack 1 communicating with another server in rack 6, what happens is that the traffic this server sends to this server over here is going to go to the top of rack switch, and then the top of rack switch will split the traffic across each spine switch. So 25% of the traffic on average will go to the switch spine 1, and then 25% to spine 2, another 25% to spine 3, and so on to spine 4. And then this switch will receive 25% of the traffic on each of its upstream links, and then these will be aggregated and sent to this server. And this equal cost multipath can be performed, for example, by splitting across different TCP connections or different IP addresses. How the load balancing is done depends on the implementation, but it's usually possible to split traffic to approach this 25% ratio on each of the upstream links. Another property of the leaf spine topology is that it's resilient to failures. Because each leaf switch has 4 upstream links, if any of the spine switches fail, then the servers in the racks can still communicate because there will be available alternate paths. When a spine switch fails, what happens is the available bandwidth decreases, but we still have alternate paths, so the communication can continue. And what needs to happen is some control software, we need to update routing and the ECMP, the load balancing, to avoid the failed spine switch. So the leaf spine topology is great for data centers, but a single layer of spine switches may be insufficient in very large data centers. And this is because switches have a limited number of ports, say 128 ports. So if we have a lot of pods, then we will need multiple layers of spine switches so that all pods can communicate with all other pods. And here we have an example of a 2-layer leaf spine topology. So this could be a pod with 4 spine switches, and then we could connect the 4 spine switches inside each pod to another layer of spine switches that's going to interconnect the pods. A nice property of leaf spine topologies is that it allows for short paths for local communication. For example, if we have 2 servers in the same rack communicating, then this communication only goes up to the top of rack switch. So with the server sends the traffic to the top of rack switch, and then the top of rack switch sends it to the destination. So this is, local traffic, which is nice. If 2 servers that are not on the same rack but are inside the same pod communicate, then again we have some local communication that remains contained inside a pod. So the server sends traffic to the top of rack switch. The destination is not on the same rack, so the top of rack switch sends it to one of the spine switches, and then the spine switch sends it towards the destination. And only when we have servers that are in different pods communicating, we have traffic go all the way up to the super spine. So here, this server sends traffic to the destination. It's not on the same rack, so this top of rack switch sends it to the spine layer. The destination is not on this pod, so the spine layer sends it to the super spine, which sends it to the right pod, and this switch will send it to the right rack, and then this switch will send it to the right server. So these local paths are interesting in that we only use bandwidth on the upper links when we are actually communicating with distant servers. And there are multiple ways in which operators connect the data center network to the rest of the internet, but one property that's common is that multiple routers are used to ensure redundancy. So when we're connecting to the rest of the internet, it's like a critical point of communication, and then 2, maybe 4 routers are used to ensure that if one router fails, the data center can still communicate with the rest of the internet.